Yeah, and like I said, sorry about there's no recording yesterday, but you know, you all that were here saw what went down. If you're dying to see what happened yesterday, you can probably look on my YouTube page and find an old night. It goes different from year to year, I guess, but you might be able to find the stuff that I talked about yesterday on an appropriate video. And if you're curious, I can try to look for that for you. So let's, oh, this is one of my favorite ones, theorem. So we talked last time about various element types. A unit, that means it's invertible, right? And from an ideal theoretic point of view, it generates the whole ring. Prime generates a prime ideal. Irreducible in a domain is maximal among proper principal ideals. Here is an important kind of relationship. You know, X and R is a non-zero prime element. Here R is a domain. Don't want to understand. If X and R is a non-zero prime element, then X is irreducible. So if you look at the non-zero elements, saying that something is prime is a stronger statement than saying that it is irreducible. Good stuff. So let's prove this. Suppose X is prime and I can factor X into A and B. Well, as X is prime, since X equals AB, it divides AB, and since X is prime, we have X divides A without loss of generality because it has to divide one of them. Hence, A equals XA prime, right? Because that's what it means for X to divide A. It means X times something is this. So here's where the domain part comes in. So what do we have? We have X minus X A prime B is 0, which is X minus 1 minus A prime B. Now, X is a non-zero prime, and R is an integral domain, right? So since X is not 0 and it's a domain of the product, these two are 0. This forces so A prime B 1. Conclusion. That is to say, well, actually, I need to think of the unit. But actually, it doesn't make any difference because they're both units, right? So, and hence, X is. So, if you have a prime, got irreducible, of course, the natural thing to ask is this an equivalence? The first definition that you all get of, the first definition of prime that you get probably in grade school or in high school, somewhere like that, is a prime is something whose only factors are itself and 1. That's okay. Primes and irreducibles are equivalent in a UFD. So when you're talking about the integers, it's all good. Can somebody give me an example of an irreducible that is not prime? Yes.
We don't take the naturals higher than 1, excluding 1.
I want it to be a ring.
Oh, okay.
You're, I smelled a mono.
Oh, yeah, sorry. Oh, yeah, sorry.
Yes.
X squared, when you take the original q join x squared and x cubed.
I like that example a lot because a lot of people will say, oh, so let me give you a couple. If you look at this ring here, and then I'll tell you why Jared's example is a bit better. If you look at this ring here, this is the set of all complex numbers. It'll look like this. This is a ring, it's easy to verify. And of course, many people see this in a first abstract algebra number theory class, and this is what everybody loves about this ring. 6 is 3 times 2. Here, this is a graduate math class. I better put up something more sophisticated. And it's also that. All right. So this thing, 2 is not a prime, right? Because 2 divides this product, right? But is it clear to you all that it doesn't divide either one of these separately? Well, that shows that 2 is not prime. But the next question I might ask is, why is 2 irreducible? Right? And it is, but there's something to show, right? Right, and use norm to show, in fact, all these players are irreducible. 2, 3, and 1 plus 4 minus 5 are irreducible, but not 5. But see, there's a little bit of a hole in this, right? Because I've got to go back and I've got to maybe verify some properties of norm or whatever. Here's another example that I think is easier to see. This is the example that should come up first, probably. Take any field and look at this ring here. Oh, what do I mean by this notation? Well, this is just all polynomials of this form. Let me put this sort of an easier way. It's all polynomials that are missing the linear term. Got linear term 0. This is actually a ring, right? Because if you take 2 polynomials that have 0 linear term, then their sum has 0 linear term. And if you multiply out 2 things that have no linear term, I mean, where are you going to get the linear term from, right? There's no place to get it, so it's still missing the linear term. Notice that x squared times x squared times x squared is equal to x cubed times x cubed. And they can both factorizations to mono in place of 6. Now, it is fairly obvious that x squared, for example, is irreducible, or I'm sorry, is not prime, because it divides this product, right? Because x squared divided x6 divided by x squared is x to the 4th, which is in this ring. But it doesn't divide either of these because there is no x, right? So this thing is not prime, but it's easier to see that it's irreducible, right? Because if you can factor x squared, what do the degree of the factors have to be? Well, you got 2 choices, 0 and 2. And that's a cheat because a degree 0 polynomial is a unit. So you haven't done anything. Or degree 1, and that can't be done at all by the way I built this ring. Actually, you can make a similar argument that x cubed is irreducible. There's just one more step to make, but it turns out that x squared and x cubed are irreducible, but not prime. So the the previous theorem in a certain sense is as good as possible. How about this one? Can anybody give an example? So this is actually, you know, when you first look at ring theory and stuff, you look at rings and say, well, yeah, it's kind of easy getting irreducible, isn't it? Right? Just pick up an element in your hand, put some gloves on maybe first, and then factor it. And now you've got smaller pieces, and just keep breaking it down until you're done. Can anybody give an example of a ring that has no irreducibles? Now I'm waiting for the smart aleck answer. Yes.
Any ring of polynomial of any field where the exponents are in U are the positive, the rational positive, rationals?
That one, that's clever, but that one probably does have irreducibles. For example, 1 plus x.
Yeah, but it has, for example, x is equal to x1 half times x1 half, and that wasn't the thing.
Well, so if I make the field say q, and then I look at 1 plus x.
Oh, yeah,
well, you probably factor that at 1/3. Yeah, maybe. I'm not sure about that, right?
So what was it?
Well, so his answer, as I understand it, is this. So I'm going to use this notation. So this is the set of things that look like A0 plus A1. Let me call it since Q1 plus A2, Q2, A, QK. Whoops, I freaked out. Sorry about that. Let me fix this. A0 plus A1 x Q1 plus A2 x Q2 plus AK x QK, where AI is in the field and QK is in positive fractionals. Is that what you had in mind?
Yeah.
It is true that all the monomials break down, right? But for example, if you have F equals Q, well, let's see here. Shouldn't make any difference, should it? I guess, let's see. If you have 1 plus X, I guess you could factor this, couldn't you? Because this would be 1 plus X 1/3, something like that. I guess I did that right. But I don't know. You might be right. I'll figure it out, but it's not clear.
I don't know. Again, I was thinking in just one element that you can factorize infinite times, not in every element that you can factorize.
Right. So so my question is, so the status of this one, I will say, is unknown for now. Yes.
What about the L squared closure of Z?
Okay, that's right. Well, here's my smart aleck. Right. Any field, because you only have 0 in units there, so there aren't any irreducibles. Okay, but if
Z and R Z bar. Z bar and C. Yes.
So this is the set of all complex numbers that are the root of some monic polynomial over Z. This includes, of course, all of the integers, but it also includes things like I, the square root of 2, all 5 complex roots of x to the 5th plus x plus 1, all this sort of thing. Here's something that's not in it, 1/2. Right? It turns out 1/2 is not not a root of this. So here, why, can anybody explain why this thing, we're gonna talk about this. Your first criticism for this might be, why is this a ring in the first place, right? Because it's probably not clear that if you take two roots, perhaps of different polynomials, their sum is also the root of a monic polynomial C. I don't think that's completely clear. We're going to see this is true later. But here's the part of the lesson where we need a little faith. So just pretend for right now this is a ring. Why aren't there any irreducibles?
If we prove that for every element in that, I mean, if we prove that element is closed under the square root, we are done, right? But,
well, that's right. And that actually, you put your finger on the right way to go about this. Suppose alpha is in Z bar, and it is okay. Let's just suppose for giggles that I have a irreducible element. So alpha is a root of monic polynomial. Let's say x to the n plus m sub n minus 1, n minus 1, m 1 x plus m0. So all the coefficients are integers. So note notice the square root of alpha is oh, I'm sorry. It should all be even. Absolutely. Notice the square root of alpha is a root of this, right? And so notice that in this ring, and it's easy to show that this is a unit if and only if alpha is a unit, right? And so if we assume this is an irreducible, then we've got a non-trivial factorization, and so this can't be irreducible, right? So this thing, if it's a ring, has to have the property that there are no irreducibles whatsoever. So if you think about my first little, why shouldn't everything have irreducibles in them? If you take something in this ring and it's not a unit, whenever you factor it, it just keeps factoring. The process never stops, no matter what you do. Okay. Any questions? Okay, so that's some elements. What I want to talk about now those sets. Okay, those sets and ideals and particular kind ideals. Now, a ring is an abelian group, and we talked about the fact that ideals are sort of like the analog, but you get group theory, they're sort of the normal subgroups. So what we want to do is there's another kind of structure that we have in here. Now, of course, what makes a ring different is the multiplicative structure. That's what separates it from being an abelian group. That's why we talked about factorization here a little bit. Multiplicatively closed sets. So looking at sets that are closed only under the multiplicative operation are actually very important. One of the reasons they come up, so here's kind of a look ahead. Again, this is kind of embarrassing for a graduate class, but what is the standard way that we add fractions? Well, we make a new fraction, and what's the denominator?
This one is
And so this would be what, AS2 plus PS1, right? So this is the standard way that we add fractions, and the standard way that we multiply fractions. So notice that when we put two fractions together, we had original denominator S1 and original denominator S2. The new denominator is the product of these two. Right? We don't really need to be able to add S1 and S2. We only need to be able to multiply it. This is part of sort of the justification of where this comes from, because multiplicatively closed sets are used in making bigger rings, usually bigger, certainly in the case of integral domains they are, called localizations, where you have this multiplicatively closed set that determines your denominators. And this, it's natural for this ring to be built because there's a very important interplay with prime ideals here. Often you want to localize, so let me give you, here's a localization that you have all seen. If I have an integral domain, then I can pass to its field of fractions just by inverting every element in there. You go from the integers to the rationals, right? By letting every non-zero integer be in the denominator. Notice what this does to the ideal structure of Z when you pass from Z to Q. In Z, you actually have a fairly simple ideal structure, but you've got infinitely many of them, right? So the ideals in Z look like this. You've got this sort of infinite crown, if you will, right? These are what the prime ideals look like in Z. Here's what the prime ideals look like in Q. Because you've let all these things be denominators, it kills their respective prime ideals. And what you've done is you pass from something that even is simpler to something much simpler. This is what localization is used for oftentimes. You got this big ring with all kinds of crazy stuff going on, but you really only care about what's happening over here. Oftentimes what you do is you kind of peel things off and turn the stuff away from where you want to concentrate your studies into units, right? And this is the idea behind localization. So let's start talking about what all this does and how the primes work. So let's suppose that ours, I don't know why I even said the domain there. So, what domain is? Oh, be a commutative ring. Not even really with this definition of any identity. And S in R, a multiplicative closed set. And S in R, a subset. And you can think this is, you can take this as a default. I usually want my subset not to contain a single element. It turns out if you localize something, set that contains zero, which you get the zero ring, you can certainly allow this, but it's just easier not to. So let's S be some subset. We say, and again, I want it to not be empty. We say S is multiplicatively closed if ST in S implies. I think this definition is very suggestive as to what it should mean. What does it mean for a set to be multiplicatively closed? It means if you pick two elements at random in there and multiply them, it's still in the set. We say S is saturated if we say that the set is saturated if whenever the product of two things are in S, then both those elements have to be in S. Let me make a couple of remarks here. First of all, many authors assume that saturated is a modifier of so when they talk about a saturated set, they will assume already that it's multiplicatively closed. There's no real reason that you do this, right? So you can consider these sort of different. It is true that the collection of multiplicatively closed sets that are saturated are important, but you can consider these as completely different things. They're sort of dual, aren't they, right? Two things in there means the product's in there, the other means that it just contains its divisors. Right? If, let me point out, if you have a saturated set in a ring with identity, then that set must contain all the units of the ring, right? Because if it's saturated, then S if one is if you have the identity element in R, S is saturated, let's say X is in S and U is in the units R, then well, XU inverse times U. Right? And so this, of course, is X. The set is saturated, so it has to contain its divisors. So it contains every unit in R. Right? Okay. So here is let's look at some more examples here. What are equal integers? So if I look at all powers of 2, what can we say about that? Is this multiplicatively closed? Certainly, because if you multiply any 2 powers of 2, positive powers of 2, you get another power of 2. Is it saturated? No. What's missing?
-1.
Well, not only that, all negative powers. But notice that given the set here that's not saturated, I can always expand to a saturation by throwing in its divisors, right?
Saturation of S.
Yes, I would call it saturation. So it will be the smallest saturated set that contains the original multiplicative set. Here's another one. Let's see if you guys can check out the pattern here. Anybody done with the settings so far?
Mine's greater than 3.
What's that?
Mine's greater than 3.
That you would think. Make sure that I don't do anything wrong here. Anybody want to venture guesses to? There's really not enough information. You'll have to get kind of lucky. And this is, of course, assuming I haven't made mistakes yet.
That's
Matrices, and factorization.
Good. Nice call. I don't really want you to know twos or threes. And hopefully I did that right up to that point. Yeah, as you can see with that pattern, I'd have to go sort of a long way before you could do anything other than guess, probably. Really. Right? It turns out, notice that this set is multiplicatively closed. And notice you can't even really check that, can you, until you get to 25 in the first place. The next place to check it will be at 35, right? It is multiplicatively closed. Well, let's see if we do this. If you have no 2s and 3s in your factorization and you multiply it together, you still got no 2s or 3s. That's what you got to learn about prime factorization. So this set, given that rule, should be multiplicatively closed. What about saturated? Well, if it contains no 2s and 3s in the prime factorization, then all it contains is basically the things that have odd prime factors bigger than 3, and that's exactly what I'm putting out there. So this is actually a saturated multiplicatively closed set. And this is all of them, right? What do I mean by that? I mean, it turns out that every multiplicatively closed saturated set in the integers is the complement of a union of prime ideals. That's another way to think about this. This is Z, all of Z, take away the ideal generated by 2, union the ideal generated by 2. And it turns out that every saturated multiplicatively closed subset of Z can be realized this way. And this set of primes can even be infinite. And in fact, there's something more true. In fact, a close analogy of this is true for general integral domains. We'll talk about that presently. Here is one of my favorite and most useful theorems. So, theorem 142. That R, B, mutable with 1, and I and R an ideal. If S is a multiplicatively closed set, just multiplicatively closed, I don't need saturated or anything, such that S misses this ideal. That is to say, this multiplicatively closed set doesn't touch this ideal at all. For example, this multiplicatively closed set and the ideal generated by 2. Then there exists a prime ideal. Piece of I containing I such that piece of I intersect S is empty. And Pi is maximal with respect to this property. And sometimes we say we can expand I to a prime maximal with respect to mixing S. Okay, so never think I'd draw a picture of ring theory class, but here I go. So here's the idea. So here's the idea. You have this elliptical shaped ring, and you have an ideal I, and you have this multiplicative set over here that doesn't overlap. You can sprinkle some fertilizer all over I and grow it to a prime ideal piece of I that is maximal with respect to the property that it misses S. What do I mean by this? Be very careful. I do not mean that piece of I is a maximal ideal. In fact, it usually isn't. What I mean is it's maximal with respect to this property. So that means if you've got any idea, if you've got any ideal that contains this, it has to overlap S. So if I throw in something else as ideal, it will make this somehow hit S, right? And I think that the proof illustrates this very well. And it comes with our friend Zorn. Okay, so the first thing I'm going to do is suppose first that piece of I is maximal, well, contains I and is maximal with respect to piece of I intercept S is empty. Now, the first thing I'm going to do is I'm going to show if I happen to have an ideal that has this property, that it's maximal with respect to missing a multiplicative quotient, it has to be prime. Okay? So that's what we're going to do first, and then we'll have to finish some things up. So
all we're assuming is that this is an ideal. Piece of I is an ideal.
all we're assuming is P sub I is an ideal that contains I, but that won't be important here. It's just an ideal, and we're assuming that it's maximal with respect to missing S. All right. Let's suppose my burden here is I want to show that it's prime. In fact, let me clarify that. Need to show piece of I is prime. So, yeah, be clear that that's what we're doing here. So let's let A, B be a piece of I. By way of contradiction, let's suppose A is not in I and B is not in spot. So what I mean by this is the ideal generated by the piece of I and A. It is the smallest ideal that contains my original P sub I and A. So everything in this ideal is in the form P plus some R times A. Am I cool with that? Now, these both must strictly contain P sub I because they contain all the P sub I, but it's also got A in it in the first case, which isn't in P sub I. It's got B in it in the second case, which isn't in P sub I. So this is slightly bigger. So what do we know then?
Contains an element of S.
Right. These hit S intersects it, right? So let's just write down what that means. So this means that there exists P1, P2, and P sub I, R1, R2, and R, such that P1 plus R1A is S1, and P2 plus R2B is S2, with S1, S2, and S. Correct. That's what it means for these to hit it. Now, there has to be some element here that's in this ideal PIA. Now let's just multiply this together. Both sides of the equation, just high school multiplication here. Now, set is multiplicatively closed. So this side of the equation lives in S, right? But at the same time, it's clear, isn't it, that this is in PI? Because P1 is, P2 is. Everybody okay with that? So is that. Why is that in PI? Right, by our assumption that AB is in here, this is also in PI. So this thing is in S intersect PI, which is the set, and then contradiction. So PI is 5. Okay, well, all right, that's the first hump to get over. What we've established is if there is a PI containing I that's maximal with respect to the property, then good for us, it's prime. What's the burden now, though? How do we know this thing exists in the first place, right? So you now show that I can be expanded to some PI maximal with respect to exclusion of S. What is it? Who do you think we need to get on the case here? It's all right. Yeah, this smells like someone doesn't. So let's let let's let gamma be the collection of all J such that J contains I, J is not ideal, and right, J intersect S is in. So what gamma is it's this big set it's a set of all ideals that contain I and miss S, right? Notice that gamma is not an empty set as I is an element of gamma. For sure. And notice gamma is a subset under set theoretic. This is like pretty much all the examples we've seen before. It's just you can compare two things, one of them contains the other. Right? Okay. Now, what do we have? We have a partially ordered set, and we want to show that it's got. I really like to have a maximal element of this. So, what do I need to do to be able to invoke the power of Zorn? Right. So let C be only about this way. J alpha set. I'm running out of Greek letters here. The chain. Right. So as before, you take J alpha and J beta, one of them contains the other. Right. And U and let U be the union of all the elements of the chain. Note J alpha is contained in U for all alpha. So we only need U to be in I said gamma. Right? Because it's clearly an upper bound. It contains every J alpha. We just need it to be in here. Okay, so what does it take for membership in this? Need to contain I. Check-a-mundo. Needed to be an ideal. We've done this before too. It's an ideal because it's a chain, right? U is an ideal as it's a union of a chain. And finally, we need U intersect S to be empty. And that's got to be true as well. Can somebody tell me why?
What's that? There would be some J that intersect with S.
If X is in U intersect S, then X is in J alpha intersect S for some alpha. Right. Because U is a union of this, so any X in U lives in one of these J alphas. Right. So Zorn's lemma applies. Zorn applies. And there exists PI maximal element. That is to say, PI contains I, PI intersect S is empty, and PI is maximal with respect. Okay, any questions on that? This is a good place to leave, but let me show you kind of the power of this. That's an ideal, and that's a multiplicative set. So there exists a prime ideal containing 0 that's maximal with respect to missing a 1. That ideal must be completely maximal, and so it follows that every commutative ring with identity has maximal ideals, just like that. Right, with the simplest ideal and a multiple set you Okay. Any questions on that? All right, well, we will pick it up on Friday.